Everyone, welcome back. So last week we calculated the heat capacity, and this time we're going to do the heat capacity again, but this time we're doing it at constant volume as a note. Okay. The V stands for constant volume, the P stands for constant pressure. And there is a difference between those two. In some cases with solids, you'll say that they're the same thing, but for metals, they do expand. For anything that actually expands appreciably, it is going to be different. So let's get right into it. So what do I care about this time? Well, there's an interesting thing. My heat capacity actually changes with temperature. So if I have my heat capacity there, my temperature here, as I know that's a capital C, I'm doing my best here. I'll see that my heat capacity starts off really low, jumps up dramatically, and then kind of plateaus off. There's a point where it just kind of plateaus off. And that point where it more or less plateaus is what's known as the Debye temperature. Why is it given with a theta? I have no idea, but it is. It is. And so the Debye temperature is typically where it goes to that plateauing where it's more or less leveled off. And before that, though, in this region, before my Debye temperature, I have a special relationship. So at that point, my heat capacity is a function of temperature. And it's a function that looks like this. Heat capacity is equal to A, make sure I write this out, yes, times the temperature cubed. And after this point, well, your heat capacity is roughly equal to 3 times the universal gas constant. Roughly. Okay, with all of that, let's start getting to the problem. So the problem tells us this. It says, for aluminum, why aluminum? Why not aluminum? It's a good one. So for aluminum, the heat capacity at 30 Kelvin is equal to 0.81 joules per mole Kelvin. And it tells us that our Debye temperature is equal to 375 Kelvin. Okay, with that, we want to know what is our heat capacity at two different temperatures. First one is at 50 Kelvin. And the second one is going to be at 425 Kelvin. So one of these is below the Debye temperature, one is above. And so that's the big thing for us. So we'll do the 50 Kelvin one first. So at 50 Kelvin, we are less than the Debye temperature, which means that my specific heat, my heat capacity is going to be equal to AT cubed. What is A? That is a constant. You have to know something to solve for it, which is why in the problem statement it gave us all the information. So since we know our heat capacity at one temperature, we can solve for A. So A is going to be equal to the heat capacity over the temperature cubed, which will be equal to 0.81 joules per mole Kelvin all over 30 cubed. So A comes out to be a very small number, 3 times 10 to the negative fifth, and that's joules per mole Kelvin to the fourth. Now that I know that, I can solve for my heat capacity at 50 Kelvin. So I just rearrange this and I say, okay, my heat capacity is equal to AT cubed. It's going to be equal to 3 times 10 to the negative fifth joules per mole Kelvin times 50 Kelvin to the third. Let's see, and that comes out to be 3.75 joules per mole Kelvin. Not bad. And then what would my specific heat be? Well, we can go ahead and calculate that. The specific heat, this is lowercase cp, would be equal to my big specific heat divided by the atomic weight of aluminum. So that would be equal to 3.75 joules per mole Kelvin. The atomic weight of aluminum is 26.98 grams per mole. And there are 1,000 grams in 1 kilogram. Grams cancels, kilograms cancels. Didn't actually have kilograms in there. Kilograms does not cancel. I'm switching, I'm doing the reverse. I was remembering the last problem. Moles cancels, there we go. And so what do I get as my value? I get 139. That looks a ton like a G. 139 joules per kilogram, Kelvin. Okay, so that was at 50 Kelvin. So now let's go to 425 Kelvin. So this is more than my Debye temperature, which means I no longer have that same relationship. Now my heat capacity is equal to 3 times the universal gas constant. So what's the universal gas constant? Well, it's equal to 8.314. It's not very good for. Let's try again. There we go. Joules per mole Kelvin. Fantastic. And it comes out to be about 24.9. Just like earlier, it's always somewhere around 24-ish, usually for metals. Now that I have my heat capacity, I can go ahead and calculate my specific heat. My specific heat would be equal to my heat capacity divided by the atomic weight, so equal to 24.9. I'll turn all my 9s into G's today. Joules per mole Kelvin, all over atomic weight for aluminum, which is 26.98 grams per mole, and there are 1,000 grams in a kilograms. So those cancels, and those cancel, my goodness. And I'm left with this, and my specific heat is 923 joules per kilogram Kelvin. And that is it. So hopefully this helps you. You can see how our specific heat and our heat capacity change with temperature up to the Debye temperature. As a note, it does change after that as well. It's just a much milder change. It's much more constant after that point. But hopefully you can see how this helps. Hopefully this calculated how Debye temperature helps us figure out which relationship to use. And I'll see you all next time. Bye-bye.